All right, so good morning. Sorry for the delay. Welcome to today's seminar. We have the pleasure of having Francesca Pina with us today. She's many of you know her already. She did her PhD here with Jesus Falcon Barroso, and then she moved to MBA, where we actually coincided for a few months, I think. And she's back since last year, I think, and now she started in September with a Marie Curie Fellow here at the ESI. And today she will be telling us about her last results on thick and thin disks. No mistake, Francesca.
Thank you very much, Nacho, for the nice introduction, and good morning, everyone. Thank you for being here today. I know this month is a bit difficult and busy for everybody. There are several deadlines at the end of the month. So I really appreciate that you're still here today. I would like also to apologize for people on Zoom and YouTube because we don't have the camera working. So yeah, you cannot see the aura and also you cannot see me. But yeah. So my talk will be on the origin of thick disks in external galaxies. I will try to convince you that thick disks are very intriguing and interesting structures. They are very important to understand galaxy formation and evolution in general. And I will then try to review just briefly what we are learning in the community in the last years about the formation of thick disks. And I will focus on my contribution in this topic, mostly showing results from interactive spectroscopy data, so from the stellar population analysis of nearby adjoint galaxies. And I will connect at the end with some results from cosmological simulations. So let's start. Okay, nice. Let's start from the very beginning. So in the early universe, we know we had already rotating stellar disks. We already had plenty of disk galaxies. These galaxies are the ones located here in the Hubble sequence. So on the left side, we have elliptical and lenticular galaxies that are also called early type galaxies. On the right side, we have spiral galaxies, which are also called late type galaxies in general. But in this talk, we will focus on these galaxies. So galaxies with prominent disks, which are located in this region of the sequence. So lenticular and spiral galaxies. So when we will talk about earlier type galaxies, we will talk about the ones in this on the left side of the disk galaxy part of the Hubble sequence, and the latest types in this, basically in this region. So in the very early universe, we already had disk galaxies. In a lambda CDM paradigm, where we have cold dark matter driving the formation of the first structures, we had the gas collapsing in the dark matter halos. And this gas already brought some angular momentum, which was inherited by the stars that were then formed. And therefore, we formed rotating stellar disks. While this is, there is more or less agreement on this, it's a bit more confusing, the measure of the thicknesses and the morphology of these first disks. There is no common agreement yet. I will mention something about new results from GWST, but yeah, there are also different opinions on this. So to measure the thicknesses of disks, we need to observe external galaxies in adjoint, so that we can analyze the vertical structure of these galaxies, and we can measure the thicknesses of disks, and we can even distinguish between different disks with different thicknesses. For example, in most of the nearby galaxies, we find a double disk structure. So this means that we observe a thin disk, which is in the midbrain region, this bright structure here. This is a schematic view of the Milky Way. Here we have most of the gas located, and we have most of the star formation going on. And the sun is also located actually here in the thin disk. But there is another structure, which is the thick disk, which is thicker and fainter. So the term thick disk appeared for the first time actually referring to external galaxies. It was in the late 70s when Bernstein understood that to fit vertical light profiles of lenticular galaxies, it was necessary to add a second profile, a second disk component with a larger scale height, which was then thicker, and that it was termed thick disk. So at the beginning, the thick disks were defined in a purely geometrical way. In external galaxies, where we have kept this definition, actually in external galaxies, so we see them projected in the sky. We only have the integrated light, and the best we can do is to observe them when they are inclined edge-on in the sky. And we can perform a morphological decomposition like I'm showing here. So we take vertical surface brightness profiles and we feed them with one bright component brighter in the midplane, this is Z, which is the thin disk here dominating in the midplane region. And from a certain height on, we have the thick disk started to dominate with the larger scale height. This height, when the thick disk starts to dominate, of course, depends on the specific galaxy. But so in this talk, we will keep this definition. We will refer to thin and thick disks as different regions in the John galaxy. So just to continue with a bit of an historical perspective, so a bit later, the thick disk was also identified in the Milky Way, or a disk with similar properties, similar morphological properties as the one found in the in external galaxies. But in the Milky Way, it was also possible to do some spectroscopy of individual stars, and therefore some specific properties were associated to the thick disk stars. The thick disk stars were found to be old, metal poor, and kinematically hot, especially compared to the thin disk. So the thick disk stars were very different from the thin disk stars. It was also found a bit later that the thick disk stars were also alpha enhanced, and somehow later, some spectroscopy was also done for external galaxies, keeping in mind that the thick disk is a faint structure, so we need deep data to extract the stellar populations or the kinematic properties of the thick disks. So when this kind of analysis was also done in external galaxies, qualitatively similar properties were also found in external galaxies. And therefore, the general idea was that thick disks are in general old, metal poor, kinematically hot, so with large velocity dispersion, with larger velocity dispersion than the thin disk, and alpha enhanced. We will see more or less at the end of the talk that this idea is a bit challenged by recent studies of some specific types of galaxies, like lower mass and very late type galaxies that are very star forming. We will see this, but the general idea is that thick disks are old, metal poor, alpha enhanced, and kinematically hot. This is what we would expect for thick disks in general. So these properties are actually what make the thick disk important to understand galaxy evolution. Because, well, if the stars are old, this means that they were formed a long time ago. Now we will see where, there are different possibilities on where they were formed, but a long time ago. So at early times, from non-enriched gas, because they are metal poor, and probably in a fast time scale. So here the alpha enhancement is usually interpreted as a fastest time scale, especially in the context of thick disks. And this is because supernova type 2 releasing most of the alpha elements and supernova type 1a releasing most of the iron peak elements have different lifetimes. And so supernova type 2 explodes faster, they release lots of alpha elements, then we have to wait a little bit more for supernova type 1a to balance the alpha elements with iron peak elements. And this is because the alpha enhancement is usually measured compared to iron. Yeah, so these properties basically, and these general ideas make thick disks very interesting and very important because they trace then the early stages of the formation and evolution of galaxies in general, in particular of these galaxies, and therefore they are key to understanding the galaxy formation and evolution in general. But let's go a bit more into the details of how we can form thick disks. How can we form then disks with the properties that we have mentioned about thick disks? One of the possibilities when the stars were formed in the same galaxy is that we had a Born-Haus scenario. So stars were formed in situ in a disk, in a thick disk of gas that formed a thick disk of stars. This probably happened in high redshift in a time where mergers, in particular gas-phase mergers, were quite common. But the second possibility is that the first disks were not already thick. We first formed a thinner disk, and with time, this disk was thickened and was dynamically heated to form a thicker disk. This process could have happened in a slow way, like more secular heating, or in a fast way with violent processes, such as mergers, for example. And the third possibility is that we had an extragalactic origin. This means that most of the stars in the thick disk were formed in satellite galaxies that were later accreted. So these scenarios were proposed in the literature to try to explain the properties that were found, for example, in the Milky Way, and then also observations try to find more hints on which one of these formation scenarios would be the most likely one. So what do we know from observations here? Of course, if you want to analyze, to know more about the structure which has old stars, which probably was from a long time ago, we have to go to the high-redshift universe, which until a couple of years ago was a bit challenging, but now with JWST we have an excellent opportunity to learn more about how disks were in the early universe. There have been already a couple of very interesting studies from JWST data. We'll focus mostly on one, which is from Tsuku et al. It appeared some months ago on the archive. And so here they analyzed different images from NIRCam at different redshifts. I'm showing here some examples. We have redshift increasing to the right side. You can see already how the morphology of disks, these are all adjoint galaxies, of course, and the morphology, you can see that the morphology changed across cosmic time. So from the right side to the left side to lower redshifts. The most important results from this kind of studies are that, while a double disk structure, so a thin and a thick disk, this means that the vertical profiles are fitted well with two different profiles, so double disk structure. This double disk structure was found already 10 gigayears ago, so very early, somehow a long time ago, but just few galaxies. In general, high-redshift galaxies, so high-redshift disks are, high-redshift disk galaxies are fitted better with a single disk. So they are single disk galaxies in general. And these single disks actually show morphological properties that are similar to the thick disks in the galaxies with two disks. So the single disks were actually thick at high redshift. Furthermore, there is a transition. So galaxies experience a transition to the double disk structure, apparently. At some point, they start to form basically the thin disk, because if the first disk were thicker, what happens later is that they also develop like a thinner disk, and they transition to this double disk structure. So this happens in general in a downsizing way. This means that galaxies with a higher mass experience this transition earlier than lower mass galaxies. This was already proposed earlier by other in previous publications. So this is very nice, and this is showing that thick disks probably formed first, actually, and that the disks high redshift were actually thick. So going back a bit to the scenarios that I mentioned earlier, this is basically ruling out the scenario of the slow and secular dynamical heating, because otherwise we wouldn't see such thick disks in the early universe. So this is very much supporting the Born-Haas scenario, the fact that the thick disk was born already thick at high redshift. Good. So JWST observations are really cool, and we are going to learn more in the next years. However, this is something very recent. And before that, we tried to reconstruct the history of thick disks with the nearby galaxies, doing some galactic archaeology with the stellar populations and kinematics. So what do we know from spectroscopic observations of nearby galaxies? The very first studies were from long slit observations. So if you know the regions where the thin and the thick disk dominate, you can see here one slit here in the thin disk and another one in the thick disk, and you can compare the properties that you can extract with the two slits. There was a very nice series of papers, which were like the pioneer studies about the properties of thick disks in external galaxies. This was from Joachim and Canton, in which they very much supported the accretion origin for thick disks in general, because in the kinematics that they found, it was necessary to add some important counter-rotating fraction of stars to explain the kinematics that they found. In some cases, this fraction was significant, and therefore they proposed that thick disks would be formed by accretion in general. Of course, these were the first studies, and they were trying to find like a common scenario for thick disks in general. A bit later on, it was proposed instead that maybe since there is a diversity of properties in thick disks, maybe they didn't form all with the same mechanisms. This diversity could be different formation scenarios and could be also complex histories. This is important because this is what was then revealed by later interactive spectroscopy observations that I will show now. So long slit observations were very nice and very important, but of course they could not provide vertical gradients, and therefore some important information about disentangle between different formation scenarios. And also they could not probe the transition region between the thin and the thick disk, which is very important to understand their the evolutionary connection between the two of them. These gaps were later filled in by interactive spectroscopy. So in the rest of the talk, I will summarize the results we have so far for thick disks from interface spectroscopy analysis, and I will take you in a journey across the Hubble sequence from the left side to the right side in the, of course, disk galaxy. So we will start with the lenticular galaxies, and we will move to the right side. If we talk about lenticular galaxies, I have to mention part of the work I did during my PhD thesis here at the ISC. This was the analysis of 3 lenticular galaxies in the Fornax cluster. This was deep muse data from the Fornax-D survey, which was ideal to extract the stellar populations of thick disks. These were the 3 galaxies here. And so I took the muse data cubes after some spatial binning. I used Voronoi binning. I used the full spectral fitting, in particular a code which is called PPXF, to extract the stellar populations. So this technique basically takes the full spectrum, the full observed spectrum, which is here indicated in black, and try to fit it with a combination of models, of stellar population models that are taken from a set of templates, which is given as an input. So in this case, I gave PPXF single stellar population models, where the magnesium over variable version of the Miller's SSP models. So from the best combination of models, which is giving this best fit, I'm showing here an example in red, we can extract the best combination of age, metallicity, magnesium over iron, because each one of these models has correspond to a combination of age, metallicity, and magnesium over iron. So in this way, we can extract something like this. So maps of age, metallicity, and magnesium over iron from top to bottom. In different columns, I'm showing different galaxies. And with these black horizontal lines, I'm showing the transition between the thin and the thick disk. So while there are some differences in the thin disks, in particular, we have, well, this galaxy here, which is overall very old, also with an old thin disk, which is something quite peculiar. I don't have time to give many details of this, but we can discuss this later if you want. While the other 2 galaxies show relatively young thin disks. So here, all ages are orange and red colors, while these green and blue colors are younger ages. So these differences in the thin disks are related to the slightly different environment of the 3 galaxies. But if we focus now on the properties in the thick disk, which are basically the focus of this talk, we see that the 3 galaxies actually show similar pattern in their thick disks. We actually have old ages in the 3 thick disks. We have low metallicities with these dark blue colors. You see lower metallicities. And the thick disks are also alpha enhanced with this, yellow, red, and orange color. So alpha enhancement. So basically here we are finding like the expected properties of the thick disks, right? So old metal poor alpha enhanced. When we started the star formation histories of these galaxies, we found something also, something very, very interesting and new. So with PPXF, we obtain as an output the weights, so the mass fractions given to different stellar population models. So yeah, here this is represented. This is an example of in a plane of metallicity age for different magnesium of iron values. We have a distribution of weights, and in this way we can also plot the mass fraction for different ages. This can be seen as a star formation history and also as an analysis of the time evolution from the right side to the left side. So from older ages to the youngest ages, this can be interpreted as time evolution. I also color-coded the age bins according to the average metallicities of the stars for those ages. And I'm showing here one of the thick disks. This is a star formation history of one of the thick disks, but in the three galaxies, we found a similar pattern. So what do we find here? We have a main old population here with some, which is the most massive one, and with some chemical evolution. So it is metal poor, but there is an increase in metallicity here. And when this component is basically getting truncated here, we have an additional component here, which is younger but more metal poor. So this was the interesting part. This was something that, at the beginning we didn't know very well how to interpret this. But then we thought, okay, but of course we cannot have this in a closed box galaxy, but galaxies are not closed box. And therefore, if you have something coming from outside, you can have a drop in metallicity. So as you probably know, from the mass metallicity relation of galaxies, you form lower metallicity stars in galaxies that have lower masses with respect to the galaxies with higher masses. So these stars must have been formed in a lower mass satellite, which was later accreted. So we found different contributions in these thick disks, which mean a complex formation, with the main population which is metal poor, but a younger population which is even more metal poor. So probably an in situ and an ex situ contribution. And we propose for the first time like these complex formation scenarios with both in situ and ex situ mechanisms in the same thick disks. Nice. This was not the first study of lenticular galaxies. There was a previous one from Sebastian Comeron et al., published in 2016. This was also Muse data. They analyzed a galaxy which was also a lenticular galaxy in a galaxy cluster, and they found a similar pattern to this galaxy that I shown on the left side of my panels. They found very old ages in general, and with somehow some different metallicities with in the thin and the thick disk, which showing that the thick disk is slightly more metal poor, and then the thin disk was probably formed almost at the same time, but slightly later. Unfortunately, they didn't extract the magnesium of iron abundances or the star formation history, so we can compare the results with those results. So this is for lenticular galaxies. Now it is natural to wonder whether we find this also in spiral galaxies. Yes. So let's move a little bit to the right side of the Hubble sequence, something like here. Actually, the very first study from interactive spectroscopy of an edge-on galaxy was done with VMOS, not with Muse. You can see here the poor spatial resolution compared to Muse data, of course. This was done also by Sebastian Comeron et al. This was 1 year earlier, so in 2015. And this data, in spite of the lower spatial resolution, was showing a sharp difference between a thick disk here. You know, the green lines are indicating the transition between the thin and the thick disk. So an old, it disappears sometimes, yeah, okay. So we have an old metal poor thick disk and the somehow younger and metal rich thin disk. So the authors propose an internal variant origin and high redshift for this thick disk. Yes, and another galaxy that I would like to show is an interesting, very massive SB galaxy, NGC 5746, for which we had 2 Muse pointings here. This was a work led by Marie Martic that we published in 2021. So for this galaxy, we, with a similar technique, also full spectral fitting again. So yeah, well, all the results that I will show from me or my collaborators will be using this same technique. And we extracted the stellar population maps of this galaxy. So this is just this part of the disk. This galaxy is very massive and large in extended in the sky. So if we want to compare with the thick disk and the thin disk, we have to look at this morphological decomposition. So the thick disk is this red region here, and the thin disk is the blue one. So if we compare with the stellar population maps, we see that the thick disk is actually old, again with these red colors, so very old actually. Metal poor, again these blue metallicity, which are lower values, and it is alpha enhanced. So especially compared to the thin disk, which is much younger, metal rich, and not specifically enhanced in alpha elements. So again, we find this pattern of this expected pattern of the old metal poor and alpha enhanced thick disk. When we start with the star formation history, surprisingly, we also find something that we found before. So basically, a main very old component and the younger little bump, a minor component. When we analyze the different metallicities of these 2 components, in this case, I'm showing this as in the plane of metallicity, metallicity H metallicity plane, and this is, so the colors are the mass fractions. So the very old component is basically this one, starting from also somehow lower metallicities with a chemical evolution. And when we reach ages of more or less 8 and 10 gigayears in this range, we find a bimodality in metallicity. So we find this component, which is metal rich, or somehow metal rich, which is the tail of the main old component. And we find at the same time a separated metal poor component. So also in this case, we propose that this galaxy had an important merger of 1 or more satellites, providing these stars were that had lower metallicities. This is the way to explain that at the same time, in the same time, we formed stars with the lower metallicity and with higher metallicities. So higher metallicity in higher mass galaxies, so in the host galaxy, and lower metallicity in the satellite, which was later accreted. So yes, also in this case, we found this complex formation with a combination of in situ and ex situ mechanisms. Now the question was, okay, but do we find this for all galaxies? What happens in galaxies that are very late type and younger in general and more star forming? So now let's jump to the, very right side of the Hubble sequence. So more or less, actually here, or even, more, because this was the very first version of the Hubble sequence, and there are currently galaxies that are classified even on the right side of this sequence. Nice. So let's jump now to a sample of galaxies very different from what we have been showing so far. This is a sample of galaxies, of 8 adjunct galaxies, which was presented by Comer et al. In 2019. 5 of them show a double disk structure. So we will focus on these 5 of them because they have a distinct thick disk. So they are what we are interested in this talk. And these galaxies are located in this plot, which is showing star formation rate as function of the galaxy mass. The sample of galaxies is located basically here. So relatively low mass, and galaxies that are star forming for their mass. Especially if we compare to this shaded area, which is from SDSS, showing that the galaxies that are star forming are located for a different star formation. So galaxies with different masses basically have different star formation rates in general. And the green valley with the galaxies that are mildly star forming are located here, so also different from different masses of galaxies. So compared to the galaxies that I showed earlier in this talk, one is NGC 5746, very massive and not specifically, not very star forming for its mass, because it is in the green valley. And the lenticular galaxies in the Fornax cluster are actually very quiescent, so they are not star forming at the moment. They are located in this range of mass. So basically, this new sample, we moved to a different region of this diagram. These galaxies are strongly star forming for their mass. They are lower masses. And something very interesting, they have extraparallel diffuse ionized gas. So they have ionized gas even in the thick disk region. We are going back to this in a second. So the kinematic analysis of this sample was presented by Comer and al. in 2019, and they showed that the kinematics of thick disk doesn't need any fractions of retrograde material to explain the observations, and they proposed the main internal origin for these thick disks. The stellar population analysis was performed by my former student when I was at MBAA, Natasha Sattler, at the University of Heidelberg. This was her master thesis, and it turned out in a paper which is at the moment under review and which is already in the archive if you're curious to look at it. So again, with the full spectral fitting technique, she extracted these stellar population maps. Here I'm showing age and metallicity, top and bottom panels, and different galaxies in different columns. So in general, in this sample, we find a range of ages different from what we have seen so far. These galaxies are low mass, so they are younger, they are still star forming, so it makes a lot of sense. This is what we expected. They are younger and they are also more metal poor. If you remember the mass metallicity relation, so we also expected that these galaxies in general would be more metal poor. Nice, but when we look at the regions that are dominated by the thin and the thick disk, which is indicated by these gray horizontal lines, I hope you can see them from there. We see that the thick disks are also relatively young, and this is something new. So if you focus on the color scale here, we are seeing that the oldest ages in the thick disks are basically similar qualitatively to the ages that we found in the thin disks of the lenticular galaxies and of that very massive SB galaxy. Regarding the chemical composition, there is no striking difference between the thin and the thick disk. The thin disk is not as metal rich as we have shown in those earlier type galaxies. Yes. Yes. Mm-hmm. Mm-hmm. This is unclear. We don't know. I think there is no common agreement about that. And there is another important thing is that when you define geometrically the thin and the thick disk, you also have in the region dominated by the thin disk, you also have stars from the other components because everything is overlapped in the line of sight. So you will also have some, for example, all stars from the thick disk, even from the halo, but yeah. So yeah, this is a bit controversial. But when we say that it is younger, it's probably that the bulk of the stars was formed later. So most of the stars. Yes, so the chemical composition of the thin and thick disk is not super different. And we see this also in the alpha enhancement. There is no specific alpha enhancement in the thick disk in this case. Very interesting, also a bit answer to that question. In the star formation histories, we see that the star formation histories of thick disks are actually extended in this case. If you remember the star formation histories that I showed earlier for those earlier type galaxies, were in the thick disks, they were kind of truncated here. They were something like this. So with a strong component for very old ages, And basically truncated here, which is when in this type of galaxies, we are forming the bulk of the stars of the thick disk. So most of the stars of the thick disk are formed there in that age. But another very interesting thing is that we have the star formation histories extended to recent times. So we have some star formation also at recent times at this height, and this is connected to the fact that we actually have ionized gas in those regions. So this is also in agreement, and this is basically supporting a different formation scenario for these thick disks. So these thick disks were not formed fast at early times at high redshift, but these results show a slow formation, probably in situ, of this thick disk because it is extended until relatively recent time. Another important thing is that from the literature, we know that there are signs of accretion of gas around these galaxies, basically all of them. So it could be that in this type of galaxies, there is now these recent times, there is still some strong accretion of gas, which is fueling the star formation not only in the thin disk very strongly, but also at the larger distances from the midplane, and also in the thick disk in the recent times, showing this connecting to these star formation histories that are extended. Good. So far, the results, seem a bit scattered because we have like small samples, individual galaxies. What we are lacking here is a systematic studies, right, of thick disks, investigating trends specifically on, for example, the stellar mass, the morphological type, and the star formation rate. We have found hints of dependencies of the cell population properties with these different galaxy properties, but there is no systematic study of trends with these properties. And this is because extending stellar populations from thick disks is quite challenging because we need very deep data because they are faint structures. So with this idea, luckily we got more than 300 hours to observe 35 adjoint Milky Way mass galaxies with the GECKO survey. So this is deep Muse data of 35 new adjoint galaxies, which is ideal. So these data are ideal to study the stellar populations of thick disks. So in this new sample, we have a limited range of masses here because they are only Milky Way mass. So we are kind of removing the dependence of the mass with the mass of the stellar population properties. But we have a large range of star formation rates. So this is an ideal sample to investigate trends with the star formation rates. Let's see what we find. So yeah, this is also in comparison to the other samples that we have been seeing. And now we will focus on the first results from a subsample of 6 galaxies, for which we have already fully reduced data because, of course, observations are still ongoing. And for these 6 galaxies, we know from my previous morphological decomposition that they have a double disk structure. So the 6 galaxies are indicated here. They have different star formation rates, and they are located above, below, and within the star formation main sequence of galaxies. Nice. So with a similar technique, also PPXF, so full spectral fitting, using models with different values of age, metallicity, and magnesium of iron abundance. Now we're integrated in a pipeline which is NGIST, which I don't have time to describe, but feel free to ask me if you're curious. It is a public pipeline to extract kinematics and stellar population in general to analyze interactive spectroscopy data, and it is just an update of a previous pipeline which was GIST from Adrian Bittner. So this is the stellar populations of the 6 galaxies, which I've ordered according to the star formation rate. So from the left to the right, with increasing star formation rate. This means that we have more quiescent galaxies on the left side of this slide, and on the right side of this slide, we see more star-forming galaxies. And again, from top to bottom, age, metallicity, magnesium over iron. Sorry for the change of the color scale, but I really like this color scale for the ages, because it kind of helps our eyes to pick very quickly what is young and what is old. So old ages here are magenta colors, and young ages are cyan colors. So in a second, you can see that magenta colors are predominant in the left side, so in quiescent galaxies, and cyan colors on the right side. So this is the first thing that we see, and also that the largest differences in the chemical composition of the thick and the thin disk are found in the quiescent galaxies. In particular, the typical pattern of an old metal poor and alpha-enhanced thick disk is found in the quiescent galaxy. You can see it here. We can also summarize these trends with the star formation rates, showing here thick disk ages, metallicities, and magnitude of iron. And here we have the star formation rate here. So the more quiescent galaxies are located in the bottom region of these plots. So the more quiescent galaxies are the ones showing the oldest thick disks, and also showing the ones that are more alpha-enhanced. While this is not happening for the more star-forming galaxies, which are also showing the youngest, relatively young thick disks. In metallicity, we don't find a clear trend. There is also a larger dispersion. These error bars are showing the dispersion of the mean properties in the region of the thick disk of the different Voronoi beams. So trying to reconnect this diverse sample with the results that I've been showing earlier, we see that the results for quiescent galaxies support a formation of thick disks at high redshift in a fast time scale, because we see that they are old, metal poor and alpha enhanced. But the results on the right side, so in star-forming galaxies, support a slower and more extended formation for the thick disks, which are much younger and with no clear sharp difference with the thin disk. Good. So very quickly, I'd like to show something about single disk galaxies. They exist. There are many of them in the nearby universe, probably like 30% could be, so far from the 50%, but they are also very interesting. They are galaxies that are fitted well with only one component, so single disk. And we have several of them, but we show just one interesting case. So this is a work done by the same student, Natasha Sartre, the University of Heidelberg, and this was her bachelor thesis, from which she published a paper in 2023. So she analyzed two Muse pointings for which we got data of this galaxy that is also an edge-on galaxy, and she extracted the stellar populations. Very briefly, I will just focus on metallicity. So in general, for this galaxy, since it has only one disk structure, we were not expecting to find clear differences in different regions, right? Because, single disk, we would expect something like more uniform. However, we found that in this galaxy, which is a young galaxy, shown by the ages, so in the early stages of galaxy evolution in general, because it is young. So this galaxy basically showed a thicker structure, which is metal poor in general, but surprisingly, it also shows this small, thinner, metal-rich structure disk in the inner region of the galaxy. This is very interesting because maybe single disk galaxies are galaxies that just didn't have time to form a second disk, as also supported by the JWST observations recently. So this could be the case of for this galaxy, because maybe this galaxy formed this like a thicker and slightly older disk, which is more metal poor, and now it is forming this inner component, which is probably what in the future will be a massive thin disk forming inside out. So this is just to show you that single disk galaxies are also important. They actually connect very well to the connection, evolutionary connection between the thin and the thick disk. So how we transition to a double disk structure. And it is also connected to the fact that galaxies form first a thicker structure, which is more metal poor. Good. So I guess we are a bit late. Maybe I can use. Yeah, a couple of minutes. Yeah, good. So this is basically what we have from observations. This is all we have, basically. We have to wait a little bit more for the upcoming GECKO's results for the full 35 galaxies, which will for sure provide some more insights on the formation of thick disks. But for now, what we can do is to complement with simulations where we can have larger samples and we can kind of travel to the past and track stars to see where they came from. So quickly, I would like to connect to some results from Auriga zoom-in cosmological simulations, which are Milky Way mass and which are relatively isolated. I analyzed a sample of 24 galaxies, which I projected also a John to allow for an approach, an analysis as similar as possible to observations, to produce mock stellar population maps. And I perform a Voronoi binning, and actually I decompose these galaxies into a thin and thick disk in the same way as we do with observations. So since I don't have time, I will just focus on two representative examples to try to connect to the observation that I've been showing. So to these two families of thick disks. The prototypical ones, which are odd metal poor alpha-NAS, and the relatively young ones. So in the bottom panels, I'm showing from the left to the right age, metallicity, and magnesium over iron of one galaxy, which has a prototypical thick disk or a prototypical pattern of a thin and thick disk. So we have an old metal poor alpha-NAS thick disk in contrast to a young metal rich and alpha poor or less enhanced thin disk. However, the other galaxy that I'm showing here has a relatively young thick disk. The galaxy is much younger in general, and we know so sharp differences in the chemical composition. So why is that? In simulations, we have the opportunity to compare this map with observations, but then to go back in time and see why this happened, actually. So we can go to previous snapshots of the simulation. So here I'm showing different snapshots from higher redshift to redshift 0. And I'm showing the surface brightness from the stars of the galaxy and metallicity in this column. So this is the galaxy with a relatively young thick disk. And we see that very early times, the galaxy is very small, very few stars. It is metal poor with these blue colors. And slightly later, so 10 gigayears ago, it is still very small, but we start to have like a primordial thick disk structure, which is starting to rotate. From that time on, so when the galaxy was still very small, low mass, we have an intense phase of mergers. In which the galaxy grows quite a lot. So thanks to this merger phase, which ends up basically here, so quite late, only 4 gigayears ago. And after that, only after that, we can form the thin disk. You can see it here, metal rich. But in the other galaxy, well, the picture is completely different. We see that this galaxy, AU18, has a fast evolution, very early times. And 10 gigayears ago, there is already a fully developed galaxy with a thick and a thin disk, quite massive already. From the time on, actually, this galaxy just keeps growing, especially the thin disk. You can see it growing inside out until redshift 0. But basically, the bulk of the mass of this galaxy was already there a long time ago. Another thing that we can analyze in simulations is the fraction of ex situ in situ stars. And from here, we can get some more hints. So that intense merger phase provided a large fraction of stars in the galaxy in general, but especially in the thick disk, where we have 50% of the thick disk which was accreted. So half in situ, half ex situ. More important, maybe more connecting to those samples in observations where we find signs of gas accretion, the satellite galaxy also provided a large fraction of a large amount of gas, fueling the star formation not only in the thin disk, but also larger height. In the other galaxy, on the other hand, we have a small fraction of accreted stars, only 7% in the thick disk, which is basically formed in situ, and actually at early time. So the thick disk was basically fully formed here. Yeah, so basically we find here these hints of how to explain the different families of thick disks in observations, because an old metal poor alpha NAS thick disks is actually formed very early time, fully formed here in a galaxy. This is very important in a galaxy with a fast evolution at early times. This is the key difference between the different galaxies. And in the other case, thick disks that are younger formed like in an extended way, and in galaxies that didn't have this fast evolution at early times, but just slowly in general in the galaxy, and probably connecting to this gas accretion, which further extended formation in these relatively young thick disks. This is all I wanted to say. The take-home messages are that thick disks are complex structures. The result from the interplay of different processes, both in situ and ex situ, probably with the main in situ formation, which provides most of the stars, but then with the later growth, which can be from more in situ formation from accreted gas or with an ex situ important component. And we have seen also that thick disks are diverse in general. They are different galaxies connected to different formation scenarios in different galaxies. In more quiescent galaxies, we have seen an early fast formation in these thick disks that are like in this galaxy with a faster evolution that are old metal poor and alpha NAS thick disks. And in other types of galaxies that are more star forming, we have this slow extended formation. So this is all. Thank you very much.
Thank you, Francesca, for the very interesting talk. I have many questions. Let's start with some. So the first one was related to the star formation histories that you are finding. I mean, it is quite intriguing, this, especially in the quiescent galaxies, this peak of a younger star formation and more metal poor star formation with respect to the older peak, no? And so I was wondering two things. First, if you see this in the analysis of the cosmological simulations, and also if you have in the data enough information to derive these star formation histories at different radii, and see whether actually there is, for example, I mean, some contribution to this small peak could be given by the flare of the thin disk.
Okay, so for the first question, we do see this decrease in metallicity also in simulations. We just see it in a slower time, in a smaller time scale, which means that it wouldn't be such a large peak as we see in observations. So we see small peaks of star formation in simulations where we have a drop of metallicity, and this is connected to the accretion of gas in particular, more than to the accretion of stars. Okay. But yeah, this difference could be because, well, we have different edge resolution in in observations and simulations and so on. But yeah, we do see that, and it is related to the accretion of gas from outside, especially from satellite galaxies. Okay. And the second question was whether
you see a radial dependence of this star formation is.
So we do see a difference. You've probably seen that in the lenticular galaxies, for example, there is a clear flaring. Yes, here. In very clear in metallicity, for example. So if you extend the star formation history in this region, for example, we do see this more metal poor component being less significant. And this is because the contamination of the flaring, probably. Because the flaring is more metal-rich stars. They were probably heated from the region of the thin disk. So the contribution of that very metal-poor stars is lower when we go to the outside region. We also mapped the distribution of the accreted stars, separating them with metallicity and these ages. And we saw that they are mostly, so the density is higher in this inner region of the galaxy. With time, they just tend to be more concentrated in the central region of the galaxy. We see also this in simulations. However, the fraction is higher at larger heights here in general, because they are like fainter structures with less stars, and therefore the contribution in terms of fraction is higher. This is what we find. And then also higher in the inner region of the thick disk than in this region.
Okay, thanks. I have another question, but I don't know if you want other people to ask first, or as you wish. It's okay.
Well, yeah, so for me, I have a question regarding the Auriga simulation that you have inside. Because have you checked that if in the two cases, the stars that were initially in the thick disk at the beginning of the simulation, do they stay there, in particular for Auriga 18? Because in some other simulation of Auriga, we see that when you have a massive accretion, you see that a lot of the stars that were initially in a disk finish on retrograde orbit. And you see this fraction actually of in situ stars having a clear drop in terms of where they're located between prograde and retrograde. And I was wondering if the stars that were initially in the thick disk stay in the thick disk, because you see also that you have a decreasing of the metallicity with ages in the upper part of the disk. So I was wondering if you have been checking this.
So you're talking about within the same galaxy, if they just migrate to a different region. We haven't checked that. Yeah. I don't think we have that information available for Riga. Of course, it's possible to do it, but yeah, it's not like ready right now. But yeah, it's a nice idea also. Well, this is a bit also a speculation, because of course we don't know. The galaxy has plenty of gas, so it could be that the thin disk keeps growing, and the reason is also because we see this happening in other galaxies, and we see this also in simulations, that the thin disks grow inside out. I think this is a model which is also very much used in the Milky Way. So in general, we expect thin disks to grow inside out. Of course, we don't know for this galaxy specifically, but yeah, it could be because the galaxy has plenty of gas to do so.
So the microphone came back to me. So I'm going to ask, of the two scenarios that you showed at the end from the Auriga simulations, so where the disk is mainly formed through accretion mergers, and the other one where it's mainly formed in situ, is there any way that we could observationally distinguish between the two? For example, do you expect any difference in the kinematic properties of the thick disk in these two cases, or any other smoking gun?
Not always. In some specific cases, it is possible. For example, we have found in the Gecko sample one galaxy. Actually, I've shown here this galaxy. Maybe I can just point to it. So this galaxy here has a counter-rotating thick disk. So when we started kinematics, the thin disk rotates in one direction and the thick disk the other direction. So we have to analyze, more into the details, combining the kinematics with the star formation history and so on of the thin and the thick disk. But we suspect that most of the thick disk would be accreted then, because it just rotates in the other way. And from stellar populations, you can do what I've been showing for lenticular galaxies. You can hope to find a different chemical composition, and in that case, you can distinguish those populations. But you can also accrete satellites with not so different chemical composition, and therefore, if you also have in the thick disk of the galaxy stars at that same age, probably you're not capable of seeing that difference so well, because it's everything integrated, and because at the same age, but maybe you have I don't know, more metal-rich stars from the host galaxy, and therefore everything is combined together. So yeah, depends on the case, I guess.
how do you decide where the limit between the thin disk and the thick disk is? It is a light decomposition, or is it by eye, or how is it decided?
So it's from a morphological decomposition. In all these cases, I took the morphological decompositions in all except one case from S4G. So this is done from in a paper from Sebastian Comeron et al. 2018. Yes, this is what I wanted to show. So basically you take a vertical surface penetrated profile and you fit it with two components. So one, the thin disk dominates the mid-plane region and the thick disk starts to dominate from here on. So I just, in observation, didn't do it myself, but I took, in most cases, the values from Comeron et al. 2019.
Well, I'll discuss with you what I think is the explanation for the young stars. Based on what we find in the Milky Way, because we don't have time now.
Okay, I think we are done. Again, thank you, Francesca, for the nice talk. And so thank you everyone for coming today, and students, please come down so that they can take note of your attendance. Thank you.